Alright, 7.7. This is hyperbolic functions. We're not going to do a whole lot with this, just the basics. And the whole premise of this is just like trigonometric functions are based on the unit circle, and the unit circle being x squared plus y squared equals 1. The hyperbolic functions are based on, if you will, the unit hyperbola. And so everything comes from a hyperbola, hence the name hyperbolic functions. You have all your definitions in here, but I'll list them quickly. When you list cosine, hyperbolic cosine, you put the h after it. Hyperbolic cosine of x is e to the x plus e to the negative x over 2. Hyperbolic sine of x is e to the x minus e to the negative x over 2. And again, you're going to notice some of the same patterns here. Tangent, hyperbolic tangent, is the hyperbolic sine over the hyperbolic cosine, which would mean if I put those over each other, the 2's would cancel out, and I would get this. Hyperbolic cotangent is the cosine over the sine, so the hyperbolic cotangent is going to be the reciprocal of the hyperbolic tangent. And the hyperbolic secant, which is 1 over the hyperbolic cosine, so I flip that one over. And then we have what left, the cosecant. Hyperbolic cosecant is 1 over this hyperbolic sine, so that's going to be 2 over e to the x minus e to the negative x. And we have a lot of identities that come along with this. And example 1 wants us to derive a hyperbolic identity. Use the fundamental identity, hyperbolic cosine minus hyperbolic sine squared, whoops, I forgot the x, is equal to 1. And we are supposed to prove 1 minus hyperbolic tangent squared of x is equal to hyperbolic secant of x. So we're starting with this, and this looks just like what I like to call the granddaddy. Sine squared plus cosine squared equals 1 when we're talking about trig functions. But hyperbolics, of course, it's got a negative there, and the cosine is first. So the first thing I'm going to do to get that identity is I need to get a 1 in the first slot and a tangent in the second spot. So if I divide everything by a hyperbolic cosine squared, I'm going to have the cosines cancel and I get 1 minus, oh, but hyperbolic sine over hyperbolic cosine is hyperbolic tangent. And 1 over hyperbolic cosine is the same as hyperbolic secant, so that's going to be the hyperbolic secant squared of x. And, oh, I wrote this wrong over here. We were supposed to be proving that it is the hyperbolic secant. Whoops. So we're done. That was part A. We proved it. Part B, derive this identity, hyperbolic sine of 2x. Oh, and this looks just like the double angle identity for trig functions. Okay, so if we use the actual definition of the hyperbolic sine and replace every x with 2x, we would get this, which then I can factor that. That would be a difference of 2 squares. E to the x plus e to the negative x and e to the, oops, extra parenthesis there, sorry, x minus e to the negative x all over 2. So now I need to have, if I take the first one and I put it over the 2, e to the x plus e to the negative x over 2, that is your hyperbolic cosine. And if I had another 2, the e to the x minus e to the negative x over a second 2 would be the hyperbolic sine. So what I'm going to do is I'm going to put a 2 over 2, which is 1, and then I can group them. I'm going to take the first one and it's going to turn it into a hyperbolic cosine. There's going to be an extra 2. This guy right here is going to be left, so a 2 hyperbolic cosine squared of x, and then a hyperbolic sine squared of x. And I'm done. I just got to turn it around. So that one's done. You have a whole bunch of identities in this section that you'll need to look at. We proved a couple of them, but they've got them all listed for you. They are very similar to the regular trig identities. Subtle differences like minus signs and things like that appear. But other than that, they're pretty much the same. You also have listed for you the rules for taking derivatives. Now the rules, again, very same to trigonometric rules. And so it says the derivative of the hyperbolic cosine of x is the hyperbolic sine of x. Now that's a little bit backwards because the derivative of the sine of x is the cosine of x. The cosine is negative sine. So we have a little bit of a sine thing here. Now if I take the derivative of the hyperbolic sine, I get the hyperbolic cosine. So there's no negative involved in these. The derivative of the hyperbolic tangent is what you would think, the hyperbolic secant squared of x. The derivative of the cotangent, and now the negatives do come into play here, hyperbolic cotangent, is negative hyperbolic cosecant squared of x. And let's get the other two down here. The derivative of the hyperbolic secant. Now, we have to make up for the fact that we didn't have a negative up at the top when we did the derivative of the cosine. So now we're going to be doing the derivative of the secant, and it's going to get a negative sign. And it'll be the secant tangent. And then finally, the derivative of the cosecant of hyperbolic cosecant. Again, negative, and this time it's hyperbolic cosecant of x, hyperbolic cotangent of x. So we see that a lot of the rules are exactly the same, subtle changes. I want to go up to the next column and I'm going to put the integrals, and the integrals are going to be the same thing, just don't forget about the plus c on the end. So that takes care of those. So in reverse, you have your integrals, and they are listed in the textbook. All right, so example 2, they want us to find the derivative of the hyperbolic secant of 3x, and it is the chain rule. The derivative of the secant is negative secant tangent, so and the derivative of the junk inside, so I'm going to put it down here, it's not going to fit there. Get a negative. We get a hyperbolic secant of 3x, a hyperbolic tangent of 3x, and then the derivative of 3x is 3, so we need a 3 in front. This was example A. Example B, now this time they want a second derivative. Second derivative of the function with respect to x a second time. So let's do the first one. We're trying to find of secant. So we start out, the first derivative would be, we just wrote it, it's negative 3 hyperbolic secant of 3x, hyperbolic tangent of 3x. So now they want us to take the second derivative, so that's going to be a product rule with chain rules in there. We're going to use this as the first, and that is the second, so negative 3 hyperbolic secant of 3x. The first times the derivative of the second. The derivative of the tangent, hyperbolic tangent, is the hyperbolic secant squared. if I write it. No. So I have that one, the derivative of the tangent is the secant squared, but it's got a junk, so it's going to have a 3. A hyperbolic tangent squared of 3x, then plus the second, and I'm going to go underneath because I'm not going to have room. The second times the derivative of the first. Well, the first already has a negative 3. The derivative of the hyperbolic secant is negative hyperbolic secant, hyperbolic tangent, but then there's a 3x, so its derivative is 3. And then there's a negative. Oops, 3x. Okay, so cleaning this mess up, I have a 3 and a negative 3, negative 9, hyperbolic secant of 3x, hyperbolic tangent squared of 3x, and then here I have 2 negatives, that's going to get a plus. I'm going to get a 3, make sure I have all my 3's here, yep, so 9, and I'm going to have a hyperbolic secant and a hyperbolic, something didn't get written right, hang on. Okay, I found the problem. At the beginning, the first times the derivative of the second. The derivative of the tangent is the secant squared. So this is supposed to be secant right here. Hyperbolic secant. I don't know if I said it and wrote it wrong or what I did, but okay. So on top, I'm actually going to have negative 9 hyperbolic secant of cubed of 3x. And then a plus, and I'm going to have a 9 hyperbolic secant, hyperbolic tangent squared. Yes. And then I could factor out a 9. I could also factor out a hyperbolic secant. And I'm going to turn it around, so I'm going to have a square of the tangent, hyperbolic tangent squared, minus hyperbolic secant squared. And that one's done. I'll finish number 2 on the next page. Okay, so now we're up to 2c. And they want us to integrate the hyperbolic cosecant squared of the square root of x over the square root of x dx. This is going to be a u substitution. We're going to choose u to be the square root of x, which means du is 1/2 x to the negative 1/2, which would be 1 over 2 the square root of x. Oops, dx. So, here is my u, so this is my u, and then this nonsense, all this stuff here, this nonsense is the du. So if I look over here, I've got the square root of x in the bottom, I've got a dx, I need a 2 on the bottom, which means I'm putting in a half. So a 2 in the bottom and a 2 on the top outside. So I have a 2 integrating. This is cosecant, hyperbolic cosecant squared of u, and the whole thing is du. And so now you say, well, whose derivative is cosecant squared on the hyperbolics? It's cotangent, but it has a negative involved. So I'm going to have a negative outside, hyperbolic cotangent of u plus some c, and so then I have to write negative 2 hyperbolic cotangent of the square root of x plus c, because I've got to put the u back in, take the u back out. Part D, integrating, this is a definite integral, from 0 to the natural log of 3, hyperbolic sine cubed of x, hyperbolic cosine of x dx. This is another u to u. In this case, we're going to use the hyperbolic sine because it's cubed. So we're going to write hyperbolic sine of x, and so du would be hyperbolic cosine of x dx. So this is going to turn into u cubed du, which is going to be easy to integrate, but I've got to change my variables. So I've got to say, all right, when x equals 0, u is the hyperbolic sine of 0. And if you go to your calculator, they should be on your calculator, you end up getting 0. Or you can plug it into what the hyperbolic sine turns into with your e to the x. Let's do the other one. I'll do this one this way. X is equal to the natural log of 3, so u is going to be the hyperbolic sine of the natural log of 3. According to my rule, the hyperbolic sine is e to the whatever I'm sticking in, natural log of 3, minus e to the negative natural log of 3 all over 2. The e and the natural log will cancel each other out, so I get 3 minus, now this is a negative in front, which means it really is an exponent, so it makes this a 1/3 over 2, so I get 4/3. Remember, with negatives in front of logarithms are really exponents on the argument. So the 3 is a -1 on the exponent, so it makes it a 1/3. So over here I have to change this to 0 and 4/3. So now I raise the power, flip it in front, evaluate from 0 to 4/3 to 0. So I have 4/3 to the 4th minus 0 to the 4th. And if I simplify that, I end up putting the 1/4 in, 64 over 81. Now, the integrals of the hyperbolics, the weird ones when you don't have the square in there, are listed, and they are integral of the hyperbolic tangent of x dx is the natural log of the hyperbolic cosine of x. The integral of the hyperbolic cotangent of x dx is the natural log of the hyperbolic sine of x plus c. Well, we put bars on it because it can't be negative. The next one is the secant. Oops, I forgot the c. And that one is the really strangest one. Tan to the -1, or arctan, of the hyperbolic sine of x plus c. And then if I'm trying to do cosecant, it's the natural log of the hyperbolic tangent of x over 2 plus c. These are some really strange ones. They're formulas for hyperbolics. I'm not going to ask you much to do with those, but they are there for us. That is in your textbook as well. So let's look at example 3. Some of them, there is a proof for the first one I gave you, the hyperbolic tangent integral, in your book, so you can see how they get proven, but I'm not going to worry about that part of this. They want us in question 3, example 3, to integrate x, the hyperbolic cotangent of x squared dx. So here we go again with the u substitution. U should be x squared, which means du is 2x dx. So I've got the x, I'm missing a 2, so I'm going to insert a 2 and a 1/2 in front. So 1/2 integral. This is now going to turn into the hyperbolic cotangent of u, and the rest of that is du. And according to my rules, a hyperbolic cotangent turns into the natural log, absolute value, hyperbolic sine, and now we're using u right here, plus c, But now I got to get rid of the u. So 1/2 the natural log, the absolute value, of the sine, hyperbolic sine of x squared plus c. And since the hyperbolic sine of x squared, it is going to be positive, we don't actually need the bars. It's not wrong to leave them, but they are not necessary. So I can just write it like this. And that one's